Good afternoon, everyone. I'm Shengwei An. Today, I'm glad to present our work Mirror, Model Inversion for Deep Learning Network with High Fidelity. This work is jointly done by Purdue University and Nanjing University. Nowadays, deep learning has achieved astonishing performance in many different tasks, especially in the image classification. We can consider a classifier as a function. It takes in an image and outputs a distribution of confidences over all the labels. There are a lot of online commercial services providing such classification APIs. Now let's first see what model inversion is. Given a model, the attackers don't know the training data or the labels. Their goal is to generate a representative image for the tight label, causing privacy leakage. For example, the attackers generated this image for the target. And then the attackers can disguise themselves according to the inverted image to pass the classification and cause security breach. There are two different settings for model inversion, Whitebox and black box. In both scenarios, the attackers do not know the labels and the training data. In the Whitebox setting, the attackers have the model architecture and height and weights. They can access the internals. They can compute the gradients. However, in the black box setting, the attackers can only get the output contents. From the left to the right, we list the results of existing methods. In each set, the first column is the target image and the second column is the inverted result. They are copied from the original papers or official GitHub repos. Since it's first introduced in CCS 15, many different methods have been proposed. The black box method AMI was proposed in CCS 19. The white box methods deep inversion and GMI were devised in CPR 20. While existing techniques have made substantial progress, there is still lots of room to improve. For example, looking at the inversion result of a ResNet 50 pre-trained on VGG phase 2, we can see features should be in the right positions, and faces should have higher resolutions and finer features for humans to recognize the target person. Since our method is based on StyleGAN, we first introduced StyleGAN. StyleGAN can generate high-resolution images from random noises called the Z-latent space. Its two main components are the mapping network F and the synthesis network G. Network F consists of several fully connected layers with the leaky ReLU activation functions. It transforms the original Gaussian latent Z space into an intermediate W space. So in step 1, we sample Z from Gaussian distribution and we generate W by apply F on Z. G is composed of multiple style blocks with various resolution scales, for example, from 4x4 to 1024 by 1024. Each style block has two convolutional layers, and the style application is achieved by mutating the means and the variances of the feature maps. So in step 2, W is fed to each style block, and a linear transformation A transforms W into styles, and those styles are used to generate the image. Now let's see how we design mirror. So we first initialize Z from the Gaussian distribution, and then we generate W. Step 2, we feed the W to the style block and generate images using the transformer styles. In step 3, we feed the generated image to a tight model. And then we use classification, and we compute the classification loss, such as using the cross-entropy loss. In step 5, we use the gradient descent method to update Z. We repeat step 1 to 5 until we succeed or we reach the maximum iterations. Now let's see how the optimization works in the Z space. The two images are real images selected from the target class. In the right, each point in the figure denotes a Z vector. We use PCA to reduce latent vectors into 2 dimensions. The green area shows the vectors sampled from Gaussian distribution. They correspond to a set of normal images generated by StyleGAN. The gray points show the trace of the optimized Z vectors at different iterations. The lighter color means more iterations. This shows the initialized Z because it's randomly sampled. It's located in the green area. For the first 4,800 iterations, the optimization stays in the green area. However, around 4,900 iterations, it becomes non-phase. And after that, it's never optimized back to normal images again. One common trick used in GAN is clipping the vectors into the dense area. Because this space is normal, so they are usually clipped into the mean minus STD and the mean plus STD. As a result, most of the points are in the dense area. However, the results are not good enough either. Therefore, we choose to optimize in W space. W space have been shown more disentangled than this space by a lot of work. So the difference here is that in step 5, we go back to the W space instead of the Z space and then repeat step 2 to 5. Although optimization in W space gives better results than Z space, the image's quality is still not satisfying. If we apply similar clipping as we did for the Z space, it does not give much improvement. The reason is that W space is not normal. Hence, the simple clipping cannot work. Observe that the left negative part of the distribution looks like compressed. Note that leaky rule will multiply a constant to the negative values. If the constant is less than 1, then the negative part will be shrinked. So let's go back to the space before the last leaky rule layer of the mapping network. It's called P space and it's normal. Now we can apply the clipping in P space to get a better result. Put them together and we have a better design of mirror. The difference is highlighted. So we added step 6, where we clip W in the P space and repeat step 2 to 6. Now assume we use the current design to invert a VGG16 model pre-trained on the VGG phase dataset. Here are 2 real images of the tight person. This is the inversion result. We find that the natural images are very different from the tight person, but the model gives them almost 100% confidence. We speculate the reason is the model overfits on some low-level features, which leads to local optima. To mitigate this issue, we apply the runtime dropout during the inference time. Dropout layers are usually enabled during training and disabled during inference. Here, we insert and enable dropout layers during the inference time. That is, we randomly set some neurons activations to 0. Finally, we get some correct inversion results. However, there are still some wrong results. How shall we decide to return which one? Confidences alone cannot distinguish the correct and wrong images. We observe that the wrong images have more diverse top 5 labels compared to the correct ones. We hence propose to select the result images according to the most consistent top 5 labels. Here we list the top 5 labels predicted by the subject model. We can see the first and third images have the most consistent labels, and we randomly return one of them. Our black box approach is similar to our white box one, except that here we use search algorithms such as genetic algorithm to update latent vectors instead of gradient descent, because we have no access to gradients. We evaluate our methods on 3 datasets and 6 pre-trained models. This table shows the accuracy and the input size of each model. When we evaluate our method, we only invert the labels which are not in the StyleGAN trained dataset. Because of the time limit, here we only show the results of our approach and the existing MI, GMI, deep inversion, and our proposed baselines, which replaces the lowest resolution GAN with high resolution PG GAN in GMI. For fairly comparing our approach against MI and GMI, we train them on the same training dataset of the StyleGAN we use. For deep inversion, its original implementation starts with random noises, denoted by DIR. We also try different initializations, such as average faces, denoted by DIA, and cartoon faces, denoted by DIC. Let's first see some qualitative results. The rightmost column shows the real images of the tagged person. For the left part, each row corresponds to the inversion results of different methods. We can see that our method gives more natural images, and our results are more consistent. This figure shows our white box inversion effectiveness. That is, can the subject model recognize the inverted images? Since it's a white box attack, we can see that almost all approaches have very high accuracy, and ours is better or similar. This figure shows the white box inversion generalizability. That is, can different models trained on the same dataset recognize the inverted images? For example, the highlighted part means we conduct a model inversion on VGG16BN trained on the VGG face dataset, and we test the inverted results on VGG16 trained on the same dataset. We can see that our approach has high generalizability. Human studies are necessary to evaluate the privacy leakage in model inversion. In order to compare our approach against baselines, we conduct a human study on the relative comparison. We want to see if humans think our approach is indeed better than baselines. This page shows the study example. We show the real image and the inverted images by our approach and the other baseline. And then we hide all images to let the user choose if the left or right image looks like the tagged person on the top. This figure shows the human preferences of our approach over others. The higher the better. We can see humans consistently think our method is better. We also conducted an absolute human study. We mix images of the tagged person and other randomly stacked people. We test that given the inverted image, if humans can recognize the target. The average accuracy is about 96%. This figure shows the qualitative results of our black box inversion. Each column corresponds to one target person. The first two rows show the real images. The third and the fourth row show AMI results and ours respectively. We can see our results are much better. We also attack online commercial services. We select 8 images from VGG Phase 2 and use Azure Cognitive Service and Clarify platform to train two-phase classifiers. We then use our black box inversion method to attack them. The results show our black box inversion can successfully attack commercial services. To conclude, we study challenges in the GAN-based model inversion. We propose StyleGAN-based model inversion in both white box and black box settings. Our method regularizes W latent vectors in P-space. We use random dropout to mitigate feature overfitting and consistent top K labels to select the correct inversions. Images inverted by mirror have substantially better quality and fidelity compared to the existing method. Thank you very much. Now I will open the floor for any questions.